Hello Nidir. Okay, I just thought we'll continue with the oscillations. We were having a good discussion last time, and I just thought that we can continue with that. And because of the lack of time, I just thought that we can make a video on it instead. We can discuss your doubts and all later in a separate thing. But yeah, for now, let's just continue with the theory of the chapter. Okay, let's quickly first review what we had discussed earlier. So we are talking about oscillations in general, and we were saying oscillations is anything that vibrates. We said it can not just vibrate like this; it can even like say speed up or say even like change shape, right? And then we said that some of these we would like to consider more than others, like the part where it looks like what we call a sine wave, right? If it's a sine wave, then it's special to us, and that is what we'll study today. That's called SHM motion or simple harmonic motion. Harmonic motion. So this is some special category of oscillation which is of interest to us. So we will talk about that a little bit more today. Apart from this, we were talking about concepts like free and forced oscillations. Uh, so one of the examples that we were talking about here was a swing, a child on a swing, right? And then we were saying that okay, if you want to push, then the right place to push a swing is right exactly at the top, as you said, and that is when the amplitude keeps increasing, right? But one thing that we notice is that amplitude keeps increasing when you push at this point, but the time period is the same. Uh, like it'll go faster, it'll come down faster, um, and then it'll reach this midpoint when it'll go very fast, and then it'll slow down and stop at the top, and then come back down, right? Okay. Uh, uh, so we called that the frequency of the external force must be equal to the natural frequency of the spring, of the swing. That is what we called resonance. So that's another thing that we discussed. Okay. If you understand all of that, then um, let's go on. So maybe we can start with the swing itself, and we can say that okay, what is the swing doing? The swing is going. So this is a swing and on the child. Swing goes back, right, where it stops. I assume that there is no motion, like the father has taken the child and pushed the swing once. So he brought it till the back and then just left it. It starts from A, then goes to B, and then goes to C, and then comes back to B, and then goes back to A, right? So if you were to say draw this diagram, then it would look something like this. If this is 0 point, this is say plus 10 point, say let's just call this, imagine this as a number line, so it goes to a higher point here, right? So let's call it plus 5, and then lower one is negative 5. Then of course like the graph starts to look like, so say the father brought it till plus 5 initially, which is point A. Then as time goes on, it falls under the influence of gravity, and so it turns out that it falls like a sine wave, in this case a cos wave. uh, it comes till here, which is point B, which is right in the bang in the middle, and then goes back down, uh, touches minus 5, and then comes back to B, then comes to A, right? So if you might notice that this does look like a cos wave, a cosine wave, right? So this is x of t, and then this is t, right? X as the function of t, x is the displacement. Okay, now if on a similar graph, say we were supposed to say what is the velocity. So instead of this here, I want to say what is the velocity. Okay, we can maybe take a good guess at it. So at this point, try to guess what is the velocity. So it has just started falling, right? But at that exact point when it has left, it is stationary. The velocity is zero. And then when it reaches B, it's going very fast, but it's going fast in the opposite, in towards the negative direction, right? So it must have gone till a negative certain value. So maybe let's call it -3, or some value -3 meters per second, right? Say I'm just arbitrarily saying. Then at C, what happens? So it stops again, right? So it stops at C, and then comes back to B. But this time when it has come back to B, it is pointing forwards. So it's the same magnitude but forwards, right? And it looks uh, something like that. So that's familiar. So it's not as it's. Can you take a guess at what graph this is? What function's graph this is? Yeah, this is a little bit tricky because sine normally looks like this, but this one it looks like it is kind of follows this pattern, right? The dotted pattern. So it looks like this is minus sine graph, right? Uh, okay. If you might notice, this is also x of t, and if you remember, cos derivative is minus sign, uh, which is why it's negative. That is expected. Okay, and then let's go on and let's finish up with the acceleration as well. So for acceleration, uh, so let's think about acceleration also. So what happens to uh, so the velocity is zero here, right, at this point, and it will start to increase towards this side slowly. That means the acceleration must also be negative, right? So it is some say negative value. So let's call it 1.3 or something, right? So this is point A. Again, let me repeat the logic. It was stationary here initially, and then when you left it, it will start to move behind. So that means the acceleration must also be behind, which made it move behind. Right? Acceleration is a change of velocity direction. At this point, the velocity is parallel. So we will see that actually at this point velocity is here, and it is not changing in a way. You can think of acceleration as this gradient of this graph. So at this point the gradient is negative, which is why this point is negative. At this point it's zero, and this point it is a positive number, right? And then it is zero here again, right? So it looks something like this, right? And so yeah, just to, and then again, like as we just mentioned, this is a d by dx relation of that. This is the derivative or the gradient of the above graph, right? So if you might notice here also the slope was zero, which is why this point was zero. The slope was um, high, so this slope was there, and then it became zero here again. So the slope again was zero, right? Okay, so this is fair enough. So these graphs are important. But one thing that we'll start to notice is what is this graph of? So this was sine, this was cosine, then this was minus sine, we said. What is this graph of? So we start to think, so cos, so since it starts from a non-zero point, it must look like a cos graph. But coses are like this, which you saw here for x of t. But it starts from, so for minus cos, it is the flipped version. So that is kind of how this one looks. So this is a minus cosine graph. And if you see these two graphs, so this is A, this is B, this is C, and this is B again. So if you look at x of t graph and A of t graph, it looks like they're just flipped versions of each other. So that's one very important observation we wrote note, that A of t is proportional to minus of the displacement graph. In fact, that is exactly one of the one of the things that makes it a simple harmonic motion. So let's just recap these things. These things can get complicated. So let's think of these things slowly. So we are trying to observe oscillation, right? So oscillation So what is SHM? SHM is basically an oscillation. So oscillation, there will be some mean point through which it passes again and again, right? So it will go left from here, then reach here, then come back, reach here, then come back, and then reach here, then come back. Those oscillation is definitely there. But the additional condition that we are saying is the acceleration graph or acceleration value must always look like the reverse, must always look like the reverse of the displacement graph. So in terms of graph, we saw that that must be flipped. So if this is how x of t looks, then this is how a of t should look. And of course, these magnitudes might not be same. That's fine. So that's one thing. Other thing is we can say that if x of t is positive, so if something says oscillating from here, which is the mean position, it goes ahead, it stops, then it comes behind, then starts to cross this point vigorously, and then comes here, and then stops here, starts moving, comes here, starts moving vigorously here, reaches this point, then starts to move here, comes here again, and then you get the point. So it's going from here to here, but it's just kind of oscillating back and forth, back and forth. It's not moving down, it's just like oscillating in place. I'm just showing you like that. So these are the places where in a way x is positive, right? So this area here is where x is positive. Here say displacement is say plus 5. At this point the all of the acceleration because of this negative uh, will be in opposite direction. So acceleration is opposite direction of x. So if x is positive in any of this region, that the force will be pulling it backwards. If the acceleration, if the x is negative in this region, then in that case, acceleration will be towards the center again. So this basically means it is always towards the center. So this negative sign makes it towards the center, and this proportionality makes it some special condition in which um, we can say that the x of t looks like a sine curve. So x of t looks like a sine or a cos. Then v of t looks like again opposites. So this is cos or a minus sign and doing derivatives. Then a of t again derivative again cos minus sign, and then sine is minus sine is plus cos. So it kind of comes like this. Try to make sure you verify how I'm going from here to here. So sine to cos, cos to sine. If we start from cos, then cos to minus sine, and then minus sine to minus cos, because cosine is minus cos. Okay, let me just repeat that. Sine, cos, cos is minus sine, cos minus sine, because of this minus sign in front, it just becomes minus cos. Okay, and as we see here, the proportionality, this just becomes a minus version of this. Okay, if these two conditions are satisfied, that it is an oscillation and it is observing oscillation in this particular form, in that case we call it an SHM. Okay, SHM is important because this is the critical thing, that x of t comes as a sine, which is what we liked as we discussed. We don't like those square forms, or like those triangle forms that we were discussing yesterday. Instead we like nice smooth sines. Okay, let's just see what a book more has to say about this, and then maybe we can take it up from there. Yeah, so we talked about how the accelerations are changing. Make sure you go through the book, it offers very simple explanations for these things. So to measure these things graphically, so we can do something like this. So let's observe this setup, what they have done here. So something like this. So let's see what they have done here. It looks like what they have done here is put springs on top of a wooden cart, and then there is a cart that's blocking a motion sensor. So that motion sensor can detect how much the distance is of the cart from this point in the motion sensor, and then they disturb the trolley and it will start to move, oscillate. So it start from negative point, it starts to move back and forth, back and forth, back and forth, and finally it stops, right? So this of course is oscillation, uh, and this of course looks like a sine wave, so it must be an SHM. Basically, it must obey this A proportional to minus x. But one additional thing that we notice here, which we'll talk about a little bit ahead, is the fact that there is, it seems to be that the, yeah, let me draw that again. It looks like the amplitude is decreasing. It started from a higher amplitude, then it comes to a lower one, lower one. You might have noticed this um, in real life also, that when you say put a child on a swing, then it stops moving after some time, right? So of course you can imagine that that is because of friction. So friction causes what we, so this phenomenon is called damping. So this is like a shock absorber example, where you set it off in motion, and then because of resistive forces it just can't keep on moving forever. So that's one more thing that we notice. So this is not a requirement for SHM, but this is an additional thing. But okay, like it still largely looks like a sine, so we'll consider it this a good example for a simple harmonic motion. Okay, if you understand this, yeah. So we talked about these things. Okay, so this also you're aware about technically. So let's quickly talk about this. You know that we defined a time period. So time period you can define from when it hits, goes here, comes back is one time period. So 1 by frequency is 1 by time period. Then we define this new term called angular frequency, which is omega, which is equal to 2 pi f in our case, which is 2 pi times frequency. It's just a definition. So it will come up later. So the way that it comes up is we say that acceleration in simple harmonic motion, now we can write an exact formula, is minus omega square x. This omega is kind of like a constant of frequency. So we notice that in a swing example, we said that how much ever is the amplitude here, like it doesn't matter what is the time period, right? So this time period determines the frequency, and that frequency determines an omega. So if time period is constant, irrespective of amplitude, then omega is also constant. So this is kind of like a constant of simple harmonic motion. So let's just write that down. Amplitude uh, doesn't affect uh, time period in simple harmonic motion. So this is one critical thing we should remember. This is very important to understand properly. Uh, so how much ever is your amplitude wouldn't affect how fast you are going through. So if you are kind of stretching it a little bit more, then it would go faster. Uh, so we can see that from the, it would go faster towards it, but as a result, the total time to cover from back to front, it will still be the same. This is something that we can see. Maybe if this is say higher, uh, then this must be higher. The forces involved, right? So this is an uh, this thing of the force, right? Hmm. So this is something like that, or we can say that if we say use a stiffer string, that is the example that a book talks about. So there is a string, and then you pull it a little bit harder, and that string is now tight, right? So imagine uh, this is the setup. This is tight. Now this is one thing, and then this is the other thing. This is setup A, setup B. You both in both the setups you pull it down the same amount. Give it to different colors. So maybe pull it down by some like 1.1 meters or something on both sides, and then you leave it. It would seem like what will happen? Can you try to take a guess? It feels like this will kind of bounce around a lot more in that same duration, right? So that means the frequency of oscillation, the time period is lower, the frequency is higher, so it frequently kind of comes down and up a lot. So which is what this thing captures. So in this case, if the forces involved are higher, if forces are higher, then the frequency here involved of the vibration is also higher for the same displacement as we talked about. So this is something that we see. So which is why we talk about this concept of an omega. I know it is a little bit tricky, but we should keep it in mind. So that's one formula in SHM. For velocity, similarly, they gave a formula that looks like. Let's just open the book here. Yeah. So that looks like plus minus omega naught square root of x naught square minus x. So let's x square. So let's just see what all are these terms. So first of all, what is x naught? X naught is the initial pull that you have done. Um, so if say this is your ball and say you pulled it till this point and then you left it. Say, let me draw it on a vertical scale. Say you pulled it towards this much x naught, then you left it and then it starts swinging. So it starts swinging from here. So the displacement is also x naught at this point. So if you put this in the formula, at this point x is equal to x naught and this is x naught. So you just put this in the formula. When x is x naught, you calculate v. You write it like this. X is x naught, then v is you can put it in. So it will become x naught square minus x naught square because this x is now x naught. So this becomes 0. Similarly, we can find what is the velocity when it comes back. Velocity when it comes back. So that at that point x is equal to 0. Now, can you find what is the velocity? Yeah, so it's plus minus omega naught x naught. So why is it plus minus? Because it crosses x equal to 0 twice, right? It comes from this point and then it is going up, then it comes back down to the same point and now it is going down. So this plus minus represents that plus and minus components. And then for completeness, let's also find what happens at minus x naught when it reaches on the top. And then you can put it in this form and you will see these two terms cancel again and then gives you the same thing back. Similarly, feel free to also find the acceleration at the 3 points. I'll just feel free to pause the video and do that. Yeah, like it's not as complicated. You can just guess key if this is 0, the acceleration will be minus times x into some constant. So minus x naught into omega square. And then similarly here this is 0 and this becomes plus omega square x. So these equations are important, and x in general follows this x naught sine of omega t. So these are the three equations that are important for us. So it either follows sine or cos, but other equations remain the same in both the cases. So either this is the yellow one or the blue one. So that just depends on, as you know, that the graph starts from the top here or it starts from the middle point here, right? So we just need to know where the graph kind of starts from. Like, have we started from the point in the middle or have we started from the point on the side? Okay. So this is all like relatively straightforward once you get used to the formulas. Try to do all of the examples here. Um, okay. And the last thing that we talk about is something relatively straightforward again. Yeah, this chapter has some equations, but you'll get used to it once you start doing the problems. They are not that complicated. So we want to see the energy now. That's the last thing that we discuss here. So when we are talking about energy, it's something like you're starting. You're imagine this kind of a setup. So you can imagine that once you do have two strings and then you pull it towards one side, then one of the springs compresses, and other one expands. In this kind of case, both this one has potential energy because it's stretched. It wants to pull it away, and then this one also is kind of compressed. It wants to push. So both of them have potential energy. But at the middle point, when it starts to move, both of them become relaxed at some point. But so all that stored energy has been transferred into the movement of the block, which is the kinetic energy in the middle, and then it goes to the left side, and where this other string becomes compressed, and then this one becomes expanded. Right, so something like this is shown here, where when you have full max potential energy, at that point you have zero kinetic energy, which is when the block is stationary and it keeps oscillating. But as a result, the sum is the same. Right, so the sum never changes. So sum is this fixed number right here at the top, never changes. But whether it is potential right now, then kinetic, then potential, then kinetic, right? So because velocity keeps changing, so kinetic energy keeps changing. So we can say that total energy is equal to when kinetic energy plus potential energy. But at some points, kinetic potential is not zero. When it is at x equal to 0, or at the median point, the middle point, right? When both of these are relaxed. So we can say that okay, at x equal to 0, half mv square, but half mv from the formula that we discussed earlier is equal to minus omega plus minus omega x naught square minus x square. So at x equal to 0, we had put the numbers before, we got it as plus 1 plus this. So v square we can find from here is omega naught omega x naught whole square. So that becomes the total energy in SHM. Total energy in SHM motion. Feel free to go through this slowly. There is more like slow explanation in the book as well. But they're relatively straightforward. We just negate the potential energy equal to 0 factor because we are considering the middle point, where all of that energy, the stored energy, has been converted into kinetic, and kinetic energy we know can be calculated from velocity, and velocity can be calculated using this formula. And of course, this x naught displacement is the secret behind why we have this total energy in the first place, which is that initial displacement that you had done. Okay, if we understand all of this, then we talked about damping a little bit. Then the last last thing we are talking about resonance also a little bit. Feel free, do try to go through this example on YouTube. The Barton's pendulum is very interesting. In a nutshell, there are things of different lengths, and you start moving one, like you move one, and all of the others don't move except the one of the same length. So say maybe this one will start to move, and nothing else moves. So this is an example where all the natural frequency is met by the forced frequency, and that increases the amplitude. Right. So if you do any other frequency except the natural frequency, the amplitudes are relatively low. But at some point, the amplitude becomes very, very high if you give the right frequency. That is what we say are the key factors for resonance in a way. So let's take all of these diagrams and put them in there. So this is the concept of resonance, right? So they are saying that natural frequency of the is must be equal to frequency of the driver, as we talked about. Then amplitude grows, and then we say that at this point it absorbs the maximum energy from the driver. Right, so you can imagine that if you're pushing at the wrong time on the swing, so sometimes you're pushing and sometimes your hand feels the swing. But if you want to push nicely, if you time it properly, then every time you just feel like you are only pushing. Whatever you are pushing, that energy from the driver, from the dial, has been is been going into the swing. Right, so The energy goes from the driver into the system, right? So this is the condition of resonance. Okay. Yeah, so that's more or less all of the chapter. So let's just talk about this last example, and then we can stop. Do read the book; it gives you some interesting examples. We have just talked about resonance earlier, so I'm not going into that much depth. Again, but the idea still remains the same. So this example is where they say is this is the example of a swinging door. So imagine that you have a door um, which has to close. So let me try to draw a door. So this door kind of opens like this and it closes. So people kind of walk in from here and then they open the door and this door kind of automatically closes. So it has kind of like a stopper, like some kind of a stopper. So now the case that they're discussing is, say if this stopper is too light, like you know that there is a weight, right, that causes it to close naturally. If the weight is too less, then it will start to close. But then say if it can swing on the other side, then it will swing and then kind of flutter around a little, right? So something like that. So this is the condition when it is under damped. So damping is when you are trying to stop the oscillation, stop the movement. This is under damped, matlab it's not enough. What happens is it kind of like bats around like a what you might have seen in movies, right? Like those doors. If you put it too heavy, then it might happen that it might close too slowly. So this is too much movement has been stopped. You wanted to stop movement, so because you did not stop enough, so it started swinging. In this case, you stopped it way too much, so it is closing very very slowly. So this is also not good. What you want is ideally what you call critical damping, where the time there is no what you can call overshoot. Here there is no overshoot, but at the same time it doesn't take too long also. So you want to balance those two things out, and in terms of how much weight you want to put here, right? So this is what again. So damping can be sometimes be good as well, and we might want that to prevent certain kind of oscillations to happen. Of course, oscillations have their good uses also. Like we talked about, heating of food, doing MRI scans are all good uses of, or watching radio or TV, as we talked about the dishes of antenna. They are good use of oscillation, but sometimes we just don't want it, so we use damping in such cases. Okay, try to attempt all the examples for this. Uh, just do how many over there are. I think there are 24. Just do all of them. There should be a lot of them are just theoretical, so just try to like kind of answer these things to yourself. And when you're done, you can upload the answers to the homework solutions drive link that I had given to you today. Okay, all the best. Have a good day. Bye.